Hello everyone, this is Monica Lupion and today I will solve one of the examples included in the lecture Heat Exchangers. This is the first example and I would like you to stop the video for a few minutes and read through the statement of the problem and try to solve by yourself. At least try to understand the data, the information that is provided. So a counterflow concentric cube heat exchanger is used to cool the lubricating oil for a large industrial gas turbine engine. The flow rate of cooling water through the inner tube is 0.5 kilograms per second, while the flow rate of the oil through the outlet annulus is 0.4 kilograms per second. The oil and water enter at temperatures of 150 and 30 Celsius degrees respectively. For the engine to operate smoothly, the oil outlet temperature should be 60 Celsius. The heat capacity for oil and water is 2.131 and 4.178 kilojoules per kilogram per Kelvin. Section A is to make a diagram of the temperature profile and to calculate the heat transfer rate. B is calculated the length of the tube, taking into consideration the overall heat transfer coefficient U. And last section, if the water flow rate doubles, how will the required tube length change? And that's a qualitative analysis. Okay, so let's first draw a diagram. So this is the example one of heat exchangers. What we have is a pipeline. Inside is water and outside it's oil. The internal diameter, it's equal to 20 millimeters, and the outside diameter, d sub 0, is 40 millimeters. We also know the temperature of the oil and water getting into this heat exchanger, and also some data about the heat capacity for oil is equal to 2.131 kilogram Kelvin, and thermal capacity for water is equal to 4.178 kilojoules kilogram per Kelvin. So section A, a diagram of the temperature profile. So let's see, we have the oil is being cooled down from 150 Celsius to 60 Celsius, so this is oil, and the mass flow rate is equal to 0.4 kilograms per second. And on the other hand, it's counterflow, so the flow is the opposite. It's water getting into the heat exchanger at 30 Celsius, so this is water, and the flow rate of water is equal to 0.5 kilograms per second. So we don't know the temperature of the water at the outlet, but the profiles of temperature will be something similar to this. Oil is being cooled down from 150 Celsius to 60 Celsius, and water is being heated up from 30 Celsius to a temperature that we don't know yet. In addition to the temperature profile, we also need to calculate the heat rate. And we can use the general formula. The heat rate is equal to the flow rate, for instance oil, because we know the temperature at the inlet and at the outlet, therefore we know delta T. We also know the flow rate and the thermal capacity here, so we have all the elements that we need. So the heat rate is equal to the flow rate of oil times heat capacity of oil times delta T of oil. This is equal to the flow rate of oil is 0.4 kilograms per second. The thermal capacity of oil is 2.131 kilogram Kelvin, and delta T is equal to 150 minus 60. And this is equal to 76.72 kilojoules per second. Okay, now in the next section, we know that the heat transfer coefficient U is equal to 50 watts square meter Kelvin, and we need to calculate the length, the area of this heat exchanger. And we are gonna use the log mean temperature difference method. So in order to apply this methodology here, we need to calculate all the different temperatures. And we know so far the inside or the inlet and outlet of oil, inlet of water, but we don't know the outlet of water. But we know how to calculate it because we know that the heat rate is equal to 76.72 kilojoules per second, and the heat that is being absorbed by the water is the same heat that is being released by the oil. So this heat here must be equal to the heat being absorbed by the water. This heat being absorbed by the water is equal to the flow rate of water, thermal capacity of water, delta T of water. And delta T of water is exactly the temperature that we're looking for minus the temperature at the inlet, which is 30 Celsius. Okay, so we have here all the elements that we need. This is equal to 0.5 kilograms per second. The thermal capacity of water is 4.178 kilojoules kilogram per Kelvin, and therefore the temperature at the outside it's equal to 66.7 Celsius. So now we know all the 4 different temperatures, 2 at the inlet and 2 at the outlet. So now we can directly apply the log-man method here. We've seen in class that the heat transfer rate is equal to the global coefficient U times the area times the delta T1 minus delta T2 log delta T1 delta T2. And what is this delta T1 and delta T2? Delta T1 is the higher temperature difference either at the inlet or at the outlet. In this case, since we just calculated that the temperature outside the water is 66.7 Celsius, this delta T is higher than this delta T. So delta T1, we need to focus in here and here. So delta T1 is equal to 150 minus 66.7 Celsius, and this is equal to 83.3 Kelvin or Celsius, it doesn't matter because it's a difference. And delta T2, it's equal to 60 minus 30, which is equal to 30 Kelvin. So now let's calculate the area in here. The heat we know from the previous section. U, it's data provided by the problem, 50 watt square meter Kelvin. This expression here, we can calculate it because we know delta T1 and delta T2. So the only parameter that we don't know is the area. So we can calculate here the area, and we know because it's a cylinder that the area where the heat transfer is being transferred, it's equal to P pi diameter, internal diameter, times L. And again, this is the surface area of the internal cylinder, because this is where the heat transfer takes place. From here, we can calculate the value of the length, that if you made the calculations, this is 468 meters. Okay? Okay, so let's now calculate or read the last section. If the water flow rate doubles, how will the required tube length change? And that's a qualitative analysis. Okay, so if we have now 2 times the flow rate of water, how will that affect to the area, to the length? And if we take a look to the equations, since the oil flow remains the same, that is, there is the same flow rate and the same inlet and outlet temperature, that means that the Q, the heat rate that is being released from the oil, remains the same. And that's exactly the amount of heat being absorbed by the water. So Q is constant. On the other hand, we know that this Q, it's equal to the flow of water, flow rate of water, thermal capacity of water, delta T. So this is flow rate of water, thermal capacity of water, delta T of water. So if we have now a higher flow rate, in order for Q to keep constant, then the delta T of the water must be smaller. And if the delta T of the water is smaller, that means that the temperature of water at the outlet needs to be smaller as well. And if the delta T of the water is smaller, delta T1, which is the difference between the inlet of the oil and the outlet of the water, if the temperature of the water at the outlet is smaller, that means that the delta T is higher. And if the delta T1 is higher, when we use the equation Q is equal to the overall coefficient times the area times delta T1 minus delta T2 log delta T1 delta T2. If delta T is higher, and the Q is constant as well as U, that means that the area needs to be smaller, and therefore L also has to be smaller.